Hello, everyone. I'll be talking about the paper titled How Likely Are Large Elections Tied? Imagine that the next presidential election is going to be held soon, and there are two presidential candidates, candidate 1 and candidate 2. There are n voters. Each of them is going to use a linear order of the alternatives to represent their preferences. And their votes are going to be represented by the random variables y1 through yn. But now let's, for simplicity, assume that these are uniformly IID random variables, also known as impartial culture in social choice theory. Assuming that everyone's votes are realized, for example, the first guy says, I prefer 1 to 2, and so on, we collect all of their votes and call it a preference profile and apply a voting rule, for example, the majority rule, which is the same as the plurality rule, to select a winner. The question is, how likely the election is tied? Well, this is probably not a very hard problem because the probability of the tied election in this case happens only when you have even number of voters, and it happens with the probability that the sum of these random variables from y1 to yn, which follows a Poisson binomial distribution, equals to exactly n/2. And by basic combinatorics, this is a probability n choose 2 multiplied by 2 raised to the minus n, and by Stirling formula, we know that this is theta going to be theta 1 over square root n. So, pretty easy problem. But the question can be asked for more general cases. For example, for arbitrary number of alternatives m, candidates, arbitrary number of agents, n, voters, and arbitrary voting rule r that has been designed and used in theory and in practice. The mathematical problems we care about is what is the probability of k-way ties under the voting rule for any k, any fixed k, between 1 and n. Who cares? It turns out that the public cares about this problem because ties can be very undesirable. For example, back in the year 1800, in the US presidential election, Burr and Jefferson ended up with a tie in the Electoral College vote. And according to the Constitution, the House of Representatives is going to vote to decide who will be the president. And guess what? There were 35 rounds of tie by House of Representatives votes, and fortunately in the 36th round, Jefferson was chosen to be the winner. And that event actually led to the change to the Constitution law. Nowadays, legislators are well aware of ties in elections and have designed mechanisms for breaking ties. And in the academic world, researchers are interested in ties in voting and related topics. For example, ties are undesirable in the context of decisiveness of voting, strategy-proofness of voting, and privacy of voting. But in a different context, ties are desirable, for example, when we talk about voting power, voting turnout, voter turnout, and so on. So this is a classical problem and it's been very well studied. So let me just highlight some classical works that are closely related to ours. And there's a wide belief that ties are rare. However, there's only limited results trying to theoretically characterize the likelihood of ties, even under specific probabilistic models. For example, EC, which is impartial culture, which is a uniform distribution over all linear orders. So past work has been mostly limited on a few positional scoring rules, and the likelihood of the ties, even under IC, has been an open question for many other rules, even after Marchand explicitly posed this as a open question 20 years ago. So personally, I can see the challenges come from two aspects. The first challenge is that the probabilistic model, especially in impartial culture, has been widely criticized to be unrealistic. And more generally, all models are wrong. So any conclusion drawn under IC or any other specific model cannot really tell us how likely the large elections are tied. And the second challenge is because of technical hardness in characterizing the likelihood of ties, even under IC and even asymptotically as the number of agents goes to infinity. In this paper, we're going to address the first challenge by analyzing the smoothed likelihood of ties using the celebrated smoothed analysis, which is believed to be a much more general and realistic model. And to address challenge 2, we're going to use Polyhedra representation of ties and an improved PMV in C theorem to do the proof. And the straightforward corollaries of our theorems answer open questions left in previous work, especially by Marchand, and gives an order over existing commonly studied voting rules with respect to their likelihood of ties under IC. So according to our corollaries, some position scoring rules like plurality, Borda, and veto, and multi-round rules like STU and Coombs have the lowest likelihood of ties, followed by Maximin and Schwarz, and followed by Max and Hairs, and Copeland, which in most cases have the largest likelihood of ties, which is constant, and that does not decrease as the number of agents goes to infinity. Okay, so before talking about the problem and the result, let me use this example to show why this is a hard problem, even under impartial culture. Consider the Borda rule, which gives you alternatives in every ranking that position I exactly n minus 5 points. For example, say we have 3 alternatives, and this is a ranking 2 prefers to 3 prefers to 1. The first alternative gets 2 points, the second gets alternative gets 1 point, and the third gets 0 point. So we can represent two-way ties between alternative 1 and alternative 2 by the following system of linear equalities, or in other words, a polyhedron. So we're going to use the random variable xijk to denote the number of I prefers to j prefers to k votes in preference profile, which is randomly generated given the probabilistic one. And the two red inequalities basically says that the total points of 1 and 2 are exactly the same in the preference profile. So if you look at it closely, the first one actually says that alternative 1, the score of alternative 1 is not less than the score of alternative 2, and the second says vice versa. The third inequality basically just says the total points of alternative 3 is strictly less. So why is it challenging to look at the probability? The challenges mostly come from two correlations. The first correlation is a statistical correlation among these x variables because they are not statistically independent, and the second correlations come from the inequalities. So the inequalities might imply each other in the general case. All right, so as promised, this paper is not just going to look at probability of ties, but also look at the smooth likelihood of ties. So here is the definition. In this paper, actually in this talk, we're going to focus on the so-called maximal adversary. Well, there's an adversary who tries to maximize the likelihood of the ties by not choosing a vote for every voter, because otherwise the likelihood of the ties is going to be, the likelihood of ties is going to be 1, but choosing a distribution for every voter from a set of distributions called capital pi over here. So we're going to use a vector pi to denote the distributions chosen by the adversary. And then on top of that, nature is going to add noise to generate everyone's realized vote, on which we're going to evaluate the likelihood of k-way ties. So this tie k RKP is going to be 1 if there is a k-way tie at profile p, otherwise it's going to be 0. For example, here, this capital pi consists of two distributions, pi 1 and pi 2. Each of them is a distribution over 6 rankings. And then the smooth likelihood of ties for 2 agents case is going to be the max of the expectation over 4 combinations. Why 4 combinations? Because we have 2 agents. Every agent can have 2 choices of the distribution. So in total, we have 2 to the 2, which is 4. Now, in this paper, we're going to make very mild assumptions on the capital pi. We only require pi to be strictly positive. At a high level, it says that it is reasonably far away from any deterministic distribution. And the second condition says that it must be a closed subset of the Euclidean space. Okay, so here's our statement of our result for positional scoring rules. It says that for any fixed number of alternatives m, any integer positional scoring rules R, which is like plurality and Borda, that gives the points to every alternative in the rankings depending on their locations. And any number of agents, the smooth likelihood of ties falls into one of the following 3 cases. The first case is 0, second case is exponentially small, the third case is polynomial. And here, the degree of polynomial is minus k minus 1 divided by 2. Remember that k is a number of ties, like k-way ties. This makes sense because it says that the larger number of ties we are looking for, the lower the probability is. And we also characterize in the theorem the conditions for each case. The zero case is not interesting. It's basically just a definition. It says that if there's no n-load profile that has k-way ties, of course, if that's the case, then no randomly generated profile would have k-way tie. The exponential case is somewhat interesting, I think. It basically says that for any distribution pi in the convex form of this capital pi, if you view this distribution pi as a fractional profile, where the weights are the probability of the linear orders, and then you apply the position scoring rule, the size of the winners, the number of winners should not be smaller than k. Otherwise, if this condition is not held, then the problem falls into the polynomial case. So let's look at an example of impartial culture. In impartial culture, capital pi has just one distribution, which is pi uni, the uniform distribution over all linear orders, and can verify that it doesn't satisfy the condition for the exponential case, because if you apply any positional scoring rule to this uniform distribution, everyone will be a winner, so the size of the winner is going to be m, and we're never going to have m strictly smaller than k. So in the IC case, we either have the zero case, or we have the polynomial case, and the degree of polynomial is as indicated in the theorem. Okay, so for the rest of the proof, I'm going to give the rest of the talk, I'm going to give you a quick proof of this theorem to kind of just show you how the general proof techniques looks like. The proof has only two steps. First step is to represent the ties as union of polyhedra. We're going to use Borda as an example again. So look at a profile P with two Borda winners under three alternatives. This happens if and only if the histogram P is in the union of three polyhedra, H12, H13, and H23. So what is a histogram? Histogram is really just a vector that comes from multiplicity of every linear order. And these three polyhedra, we actually have already seen one of them. For example, H12 represents the cases where alternatives 1 and 2 are the Borda co-winners, which are represented exactly by the system of three inequalities we have seen earlier in this talk. And similarly, H13 and H23 represent 1 and 3 are the co-winners, and 2 and 3 are the co-winners, respectively. In the second step, we're going to prove and apply an PMV in C theorem. So what is this theorem about? Well, so first, PMV stands for Poisson multinomial variable, which is the histogram of n independent but not necessarily identically distributed random variables, y1, y2 through yn. Each of them is over q numbers, 1 through q. So this PMV is characterized by a vector of n distributions, pi1 for y1, pi2 for y2, and pi n for yn. And in the PMV in C problem in this talk, we want to characterize the maximum probability of our PMV in this union of polyhedra. So for the interest of time, I'm only going to present the proof for the special case where C consists of just one polyhedra. And actually, this can be very easily leveraged to the union of polyhedra. So this is really the key part of the proof. So in the PMV in polyhedra theorem, we're given any polyhedron H characterized by an integer matrix A and any vertex B. We're going to let H0 denote its characteristic cone, which is obtained by replacing this B vector by the 0 vector. Take Q equals 2x as example. Say we have an polyhedron H over here, and H0 is basically obtained by just shifting the boundaries to the 0 point. Now, the theorem claims that the maximum probability for PMV to be in H is one of the three cases: 0 case, exponential case, and polynomial case. So what's interesting about this theorem is that we have asymptotically tight bound for the polynomial case and the characterization of the degree of polynomial. Here, the degree of polynomial depends on two things. It depends on the dimension of the characteristic cone, which is the dimension of the smallest linear subspace that contains H0, minus the Q, which is number of options. So here Q equals to 2, but in general, in voting setting, Q equals to n factorial. Okay, so the case for condition for exponential case to happen is H0 is the intersection of H0 is in the convex hull of pi is empty set. So let me give you an example of the polynomial case. Suppose the capital pi consists of two distributions, pi 1 and pi 2, and then the convex hull will be just the linear segment between them. You can already see that the convex hull, the intersection of the convex hull and H0 would have one point in common, which is pi 2. So that means if this is our capital pi, the problem falls into the polynomial case. So how should we prove this theorem? Well, the zero case is trivial. The exponential case is actually easy and can be proved by existing techniques. And the most complicated and the case, where a non-trivial case, would be the polynomial case. So this is how, at a high level, how this is proved. Suppose you are an adversary. In this case, you can choose a vector of pi that is hopefully as close to h as possible. And all you can do is that say, let pi hat denote the sum of this pi vector, of these pi distributions, like pi 1 through pi n. We know that pi hat must be in the convex home generated by this capital pi, basically the shaded areas over here. And the concentration theorems would tell us with high probability, the P and V would fall in an theta square root n neighborhood of pi star, of pi hat. And because of the condition of the polynomial case, this pi hat is going to be O1 away from H, or maybe this pi hat is in H itself. Now, the real challenge is to calculate the probability for the intersection of this area and H. And actually, this is a place where the standard central limit theorem are two cores, because all of them, as we are aware, have a 1 over square root n error, which is two cores for the bounds we're trying to prove. So we prove new pointwise concentration and anti-concentration bound, and we count a number of points here to prove the polynomial case. And after we have proved this theorem, we're going to apply it to the unions of H in the polynomial to prove the original theorem. All right, so quickly summarize the talk. We have analyzed the smooth likelihood of the ties in this paper, and we just show the proof for the position scoring rules and the proof for other rules, and the mean adversary case are in the paper. So for future work, we can think about three directions, like smooth the social choice problems, like smoothing possibility theorems, axiomatic approaches, and computational problems. Thank you, and I'm looking forward to your comments and questions.